All right, so the first thing I'm going to do is I'm going to separate the variables. Notice that the function is y. Y is like the amount of the population, and then the independent variable is t. So when I do the separation, what I'm going to end up doing here is I'm going to end up dividing both sides by y and m minus y. And I'm going to end up multiplying both sides by dt. So the dt's are gone here, m minus y and y are gone here. So what I'm going to have now is a k and a dt on the right, and then a 1 over y m minus y dy on the left-hand side. And then I'm going to integrate both sides. Now the right-hand side is just kt plus c. Antiderivative of k being a constant with respect to time, kt plus c. The left-hand side is going to require a little bit more work. So I'm going to come off to the side here, and well, I guess I'll just do it right here. We're going to have to do a partial fraction decomposition on the left-hand side. So I'm going to have, well, I guess I'll do this over here. I'm going to have 1 over y m minus y is going to be equal to some constant a over y plus some constant b over m minus y. And then I'm going to work out the a and b. So I'm going to multiply through by the common denominator. So I'm trying to split the fraction. So I'm going to multiply through by the common denominator, and I end up with 1 is equal to a m minus y plus b y. So I took that equation there, and I'm trying to find the a and the b, and I'm just going to multiply through by the common denominator of y m minus y. All right, so then I'm just going to choose some values for y to determine what a and b are. So let's assume that y is equal to 0. If y is equal to 0, then the equation says 1 is equal to a times m, thus a is 1 over m. And if I let y be equal to m, that will cancel out the a, and I'll get 1 is equal to b times m, or b is equal to 1 over m. So both a and b are both equal to 1 over m. Now remember up here, m is called the carrying capacity. When you start out with a logistic differential equation, something of this form right here, get rid of this. You're always going to end up with your a and b being 1 over the carrying capacity. So when I come back to my integral now, on the left-hand side, really what I'm integrating is a over y plus b over y, m minus y with respect to y. And the 1 over m is in common, is the a and the b, so I can just pull that right out in front and put 1s in the numerator. So left-hand side now, I'm going to have the following. 1 over m, the antiderivative of 1 over y is ln absolute value y. And the antiderivative of 1 over m minus y is minus ln absolute value m minus y. And the minus here is coming from the fact that the derivative of the inside is -1. So if you take the derivative of this, you end up multiplying by -1, which cancels that out. And then I've got my KT plus C on the right-hand side. So I'm going to do a couple things here. I'm going to multiply, well, do I want to do that? Not yet. I'll just leave it the way it is for now. But on this, well, I guess I might as well do that. I'm going to multiply through by 1 over m. So when I do that, by m, I'll end up with mkt plus m times c, but c is really just another unknown constant, so I'll just leave it as plus c plus an unknown constant. And then I'm going to, on this side, on the left-hand side here, in the parentheses, I'm also going to combine those logs together. So I'm going to have the natural log of y over m minus y in absolute value is equal to mkt plus c. Now, I need to solve this for y. So I'm going to raise both sides to the power of e. And when I do that, I'm going to end up with the absolute value of y over m minus y is equal to e to the mkt plus c. I'm going to drop the absolute value by applying plus or minus to the other side, y over m minus y. Let me fix that. Y over m minus y is equal to plus or minus e to the mkt plus c. Now again, I'm trying to solve this for y. So I'm going to next, see how much room I have here. I got one more step. I'm going to take the reciprocal on both sides. So when you take the reciprocal on both sides, you're going to end up with, why can't I switch pens? There we go. M minus y over y is equal to plus or minus. Now, this side is just an exponential function. So I can take the reciprocal by just negating the exponent. Like so. So I just took the opposite of the exponent. All right. Now, the reason I took the reciprocal on both sides is I can now split the fraction on the left-hand side. I'm going to have m over y minus 1 is equal to plus or minus e to the negative mkt minus c. Now, I can, at this point, I'm going to do a little bit of a rearranging here. I'm going to add 1 to both sides. I'll have m over y is equal to 1 plus or minus. And now I can rewrite the e to the negative mkt minus c as e to the minus c times e to the minus mkt. And then I'm going to do a substitution. Let me see, what variable did I end up using up here? I used just a big capital C, so I guess I'll continue to use that. Yeah. All right. So I'm going to just let capital C be equal to plus or minus e to the negative c. So reason I'm doing that is because I'm just trying to simplify this. So I'm going to have m over y is now equal to 1 plus c e to the negative mkt. Now, reciprocal on both sides, y over m is equal to 1 over 1 plus capital C e to the negative mkt, and then multiply both sides by m. Y is equal to capital M over 1 plus C e to the negative mkt. And that is my general solution right there. Now, let's compare that to what I have written up here. And you'll notice that I have capital L's in here, and that, now that I look at this, that is a little bit of a typo, because what I mixed up my what I'm using for my carrying capacity. So in some textbooks they use M, and in some textbooks they use L, and somehow I managed to use both of those. So let me fix that. And make these into what they should be, which are capital M's. Okay, so sorry about that. So you see the solution to the logistic differential equation looks like this. Y is equal to m over 1 plus CE to the negative KMT. Make sure I have the same thing down here. M over 1 plus CE to the negative MKT. And if you look at this, if you take the limit as c goes to infinity, what happens here is this goes to e to the negative infinity, which approaches 0. You end up with m over 1. And so the limit is m, which makes sense if you think about, we know what this graph looks like. So as time goes by, this thing is going to get closer and closer and closer to approaching the m. So the y value here, the population value, is getting closer and closer to m. The limit as t goes to infinity of the derivative is equal to 0, because as time goes by, the population gets closer and closer to its carrying capacity, and that slope right here is approaching 0. So the change goes to 0. The derivative is a maximum when y is equal to m over 2. So if you look at the slope here, the slope of this graph starts out small, gets bigger and bigger and bigger, and then about right here, the derivative reaches a maximum, and that's actually an inflection point. You can see on the graph that the function is changing from concave up to being concave down. That always happens when the population is at exactly half of its carrying capacity. So the reason I bring this up is because this is a common question on the AP test, where they'll ask you, where's the inflection point on the logistic curve, or when does the logistic curve, what does the population reach or growing at a maximum? Sorry, that's the term I'm looking for. When is the population growing at a maximum? Well, it's when the derivative is a maximum, which is always when the population is m over 2. All right. So now that we've solved the entirety of the logistic differential equation, the next thing I'm going to do is then we'll use that solution to go through this question here.